Have you encountered any resistance from people who like their quantum mechanics mystified?
Mystified. Yeah, they like it shaken, not stirred, right? I mean, a little bit. Yeah, I think it's so there's a sense in which this picture is deflationary. It deflates. It takes exotic statements, oh, the cat is alive and it's dead, and it deflates them and says, actually, it's really one or the other. And we merely represent it mathematically with a state that looks like it's a superposition of live and dead because it gives us divisible evolution we can use. It's easier to study mathematically, but it's not the reality. It deflates.
This man just breaks Schrodinger's cat. We continue.
It's that, yeah.
Just to be clear, deflationary is the philosopher's term for saying there's nothing to see here, folks. Just calm down.
Yeah. It's basically that. It just like sucking the air out of the balloon, right? It brings it down to earth, which is basically what this does. It makes quantum mechanics, I think, in some ways much more boring. And, you know, as I was working on this, I kind of felt that because when young people go into physics and they begin learning about quantum mechanics, it's super exciting to think that you're going to be able to understand what's going on when the cat, Schrodinger's cat, is alive and dead, and you know, particles can go through both holes in the interference experiment at once, and it interferes with itself, and you know, everything is entangled with everything else, and maybe when we think about things, we humans are special, we collapse things. This boringifies quantum mechanics.
Okay. All right, we'll stop. We'll stop reusing Kurt's content from there. The links in the doobly-doo. It's a fascinating conversation, but we'll pull them out. We'll do the very beginning, because. All right. I figured we just lay in with that just because this is fascinating, and anybody that actually clicked off the algorithm actually recommended something called what is non-Markovian. Why? Okay. So the whole part of all this, all right, there's still some stuff on the board from some discussions. We can touch upon that in a moment there. But well, nerdy, that might be a true statement. He's commenting, my future self influenced the past to bring me here now. Now, I can neither confirm nor deny that. Okay, that starts breaking the brain. I start getting an error 404 if I need to delve into that because. Not a big time travel guy. Well, except for just what we're doing right now. Some may say, I think Professor Wolfram on Professor Keating, they had a chat that was published this morning on Professor Wolfram may claim that time is the inexorable processing of computation. Now, I know there's some big computational fans here. I am kind of biased to that, and then you do some calculations, you're like, this might make a lot of sense. So, but that's not why we're here. Non-Markovian, what is that? Full disclosure, I don't know. My best zeroth level approximation from the little bit of stuff I've gone on to, it means time matters. What am I talking about here? Okay, so apparently your standard Markov chain or whatever it is, your Markovian dynamics. Basically, if you took a screenshot, if as Brad Voorhees from the Sonic Gravity podcast might say, is you took reality in every single instant of time, imagine it like a slice of cheese or a flip book, something like that. Something that our human brains can go, basically, if you just froze everything and you were to measure and have all the information, you could tell what was going to happen next. The whole non-Markovian process, it means that you, in order to actually know what happens next, you must have the past, which is an interesting thing. I still have a hard time trying to fully grok what that means, but we're going to delve into some stuff and things because maybe it's just me. Maybe it's just because I've heard the term and now I'm a very excited little memes here saying, oh, this non-Markovian process. But now that I am conscious of it, and I see this thing come out with Kurt, and I start looking into Professor Jacob Barondess's different talks and everything, the man who bornified quantum theory, pardon, because I'm sure nobody else like me has used quantum theory and quantum mechanics interchangeably because Well, that happens to be the primary method of the standard model, in order that we've literally created the standard model. We put this recipe into a magical black box and it gives us the correct probability distributions. Why? Nobody knows. That might be a lie, because apparently, we'll recap as other folks are joining us right now. But essentially, Professor Barandas of Harvard, he was trying to do an intro to quantum mechanics for some first year physics students, and he's like, "All right, well, let me create a little presentation. Let me take the classical world that we have. Let me take the quantum world, and we got this chasm in between them." He's like, "Let me follow this chasm around and like see where the gap is, and I'll focus on that gap." But surprisingly, he made a mistake. He did not fully consider all the Markov. He didn't know he needed to be bound by Markov dynamics and everything like that, because apparently that is and or was an axiom of quantum theory. Again, I am not a professionally trained physicist. Verify me, correct me, please. But essentially, it was assumed that you needed some Markovian style process, because that's what we have and everything. And we're able to account for what the state might be. It seems to work. Apparently, he didn't do that. And he followed that chasm down and the chasm disappeared. So it essentially sounds like the gap between classical mechanics and quantum mechanics, you can kind of just see it. There ends up being an emergible state, so to speak, because the way he ended up phrasing it was, some folks may say, Bohmian mechanics. You'll hear that term, hidden variables. Now, hidden variables is the more negative connotation of additional variables, which, i.e., information that we don't know about yet. Perhaps that's because there ends up being some emergible state. Insert rampant speculation right here. I'm thinking it's about at the 7th decimal place, probably about 10 to the negative 7. If anybody else watches Fractal Woman, you're going to find her, what is it, modified unit analysis, that she's trying to redo all the stuff on Codad and everything. Think she is using that in her construction, but also I'm wondering if she's going to notice around the 7th significant digit things kind of start to get weird, because I don't think there's a lot of people out there. I only know one, Thad, that's actually gone through, looked at these numbers and everything, these constants of nature, and tried to find interesting things and noticing, oh, wait a second, these numbers don't seem to match once you get around this magnitude. Maybe there's something interesting going on. Okay. But we've got a few more folks joining us. Oh, we got Ernesto. Yes. Basically, that's the thing. I think the best example they give is something of, what is it? They give, like, you got a pocket full of change. It's like $3 or something like that. You have X number of quarters, X number of dimes. If you knew quarters were taken out and you were to guess the probability of the state, you'd be able to rule out certain things. Either that or like the cup game and stuff. So it's like, all right, if it's under this one, you're moving around. If you pick one cup, okay, maybe that isn't a good example. Again, I am not a statistician. We have XYZ. Yes. Not at all. You're looking at a crazy person on the internet. But if there's one thing I've noticed, it's crazy people can notice things too. And some of the craziest people seem to be very famous people nowadays. But at the time, they died penniless and alone. Hopefully that doesn't happen again. Well, that's just history. But we will continue onward. And let's do this little intro again. And we'll embiggen it a little bit. There we go. We're embiggened. Basically, the long story short, in the quick, snappy, totally clickbaity style.
I didn't know it was impossible. So I brought these theories closer and closer together, expecting that there would be a moment when I would need to make some kind of jump to get from one theory, classical physics, to the other theory, quantum physics. And the strangest thing happened. The two cliff faces merged, and there was just no chasm anymore.
Yeah, I know. The man who bornified quantum mechanics or theory. I digress. Okay. All right. So the thing that got me is, okay, I'm looking into some of that, I'm listening, I'm going through, I'm like, all right, well, I seem to be able to actually start to follow this. And again, it's not that I've taken all the multiple semesters on quantum mechanics. It's like, all right, something operates. But I'm like, all right, I'm just gauging it. I'm like, he's on the Harvard Foundation of Physics YouTube channel. So I got like 700 or so subscribers. I mean, hey, you do what you want. Um, and he's on the Harvard Physics channel. He's been talking about this stuff for about a year or two. I'm like, okay. He's apparently on like, he does not seem like the random person that's like, I've totally solved everything and I'm just coming out and just saying a bunch of things. He's going through the formalisms. I don't hear any really people saying that he's wrong. I mean, maybe it's just confusing. Maybe nobody really understands, but it sounds like he's using the keywords are unistochastic process and non-Markovian dynamics. Okay. So why am I even talking about this? And why did I have Anton in the thumbnail there? All right, we're going to get to that next. Because you got our good friend Anton. He's in. No, no, no. Of course, I closed out Anton. But essentially, we'll go over to. We already had his quote that was relevant here. So let's actually just go to. Where's the paper? Did I get rid of the paper? I closed the thing with the paper. What a terrible human being I am. Okay, so I'll just bring him back up. Boom. And that is physical review A? No, this is the one where I was locked out again. Oh no. What is he doing? He's ruining everything again. Bill history. Go back and Markov. Exact quantum electrodynamics of radiative photonic environments. Okay. Here. Yes. Sorry. We're going to bring up a paper. Don't be scared. All right. Here we go. The link is in the doobly-doo. All right. So what the heck is this thingy here? Okay. So according to this paper, it was in physical review letters, we have exact quantum electrodynamics of radiative photonic environments. What the heck is that? Let us read on. We have Ben Ewan and Angela Damatrido, School of Physics and Astronomy, University of Bern. All right. We present a comprehensive second quantization scheme for radiative photonic devices. We canonically quantize the continuum of photonic eigenmodes by transforming them into a discrete set of pseudomodes that provide a complete and exact description of quantum emitters interacting with electromagnetic environments. That sounds quite precise. This method avoids all reservoir approximations and offers new insights into quantum correlations, accurately capturing all non-Markovian dynamics. This method overcomes challenges in quantizing non-Hermitian systems and is applicable to diverse nanophotonic geometries. Okay, so that was a whole bunch of words. What does it mean? Again, time matters. Time matters. But I just find it interesting because I'm listening to something. It sounds like, all right, maybe we broadened the axioms of quantum theory, and there may be new, perhaps somewhat more traditional methods forward that could be employed. And again, that would require an enormous amount of work. I mean, it would be really cool if some folks were working on that. I'm just saying. But if we have the ability to move forward, and just quick interjection, totally biased, of course. Something that Jacob Barandas had mentioned, something about, I believe, the product of Cartesian planes or something like that. I'm like, wait. Product. Isn't that like your multiplication thingy? So you're multiplying a plane, you're multiplying another plane, and you're going to get out something that's hopefully going to reflect what we actually measure in the real world. Only somebody's working on that. So this got to me because Anton was talking about that. He was going on because apparently they've utilized this new method, and before you're hearing people say this is a picture of the photon, people probably remember that yin yang symbol with like, oh my god, the photon, it's just a dang yin yang. Look how obvious it is. See, I'm not gonna lie, that would be pretty cool. And I'm not saying something about like a couple of circles and maybe coming together and forming a knot might actually explain that. But no, they were taking a picture of a yin yang symbol, but they were using a particular method of photometrics or photography where basically they were, what is it? You had a state here, and they were trying to measure it from another state. I think we covered it at one point, maybe like a year or so ago, whenever that happened. But that was not the actual picture or model of a photon. Those are photons being used to take a picture that everyone's like, oh my God, it's the yin yang, duh. Okay. A little bit more involved with that. Not gonna lie, if that does end up coming to be a better model, that would be really cool. But where was it? Okay. So rather than let's read a bit of the paper. Let's see. Uh, where is this at? Oh, I thought you said I thought Nerdy was commenting quantum retrocausality. It's where it's cat. Now, and that's coming from a rodent YouTuber who occasionally has a pickle form. But a lot of I don't know enough on that, Ernesto, to say whether that's true or not. I'd say that would greatly enhance one's ability just because you're minimizing the stochasticity there, I believe, just because if you have a whole bunch of moles and moles upon magnitudes of moles of air and stuff in there, yeah, it's going to add in some new dynamics. I mean, it might be minimal on our scales and everything, but it's, nobody's ever blown a pool ball in before. Like that was it the quarter-inch blow rule? That's it is what it is. You play by your house rules. But where was that? Oh, go back to yes. All right. Let's do a little bit of reading. Let's embed in it. Okay. All right. So this is only a 6-page paper, and the last page is basically like references and stuff. So it's actually not that long. Maybe we'll just read it here. As the geometry of the environment defines a photon's interaction with matter, bringing complexity to its radiative behavior, from the Casimir force between an atom and a surface, or the enhanced fluorescence of a molecule by a nanoparticle, to the tapestry of colors scattered by the stained glass. Lastly, quantum emitters, QEs, such as atoms, fluorescent molecules, and quantum dots have been coupled to ever more geometrically complex photonic devices, such as optical microcavities and nanobeams, plasmonic and nanostructures, and hybrid and nanophotonic devices. The interplay with multiple photonic modes of varying radiative behavior leads to non-Markovian quantum dynamics. Such dynamics significantly impact the future development of quantum information processing, quantum transport, photochemistry, and biological processes such as light harvesting. I'm sorry. I just got a picture there for a moment of just, we're out there. The light is yay high. Pull out your size, y'all, and let's. I then realized I'm probably talking about solar collection devices. Yeah, that's what happens when you watch too much anime. You're imagining Goku Black going out there. I harvest all the light before I rain down. Yeah, but I digress. Mark, no. That's the thing. Be wary. If there's one thing I've learned from Dr. Eric Weinstein, should avoid teaching. I'm simply here to learn with the rest of y'all. That's why we're learning in class. Also because I'm not good at doing extra homework. I still have assignments I've been procrastinating on. We harvest. Well, it might be into the storage capacity, but literally, good old gravity is helping with that. It's like we use the light. We're collecting this energy. We need to store it. What can we do? Let's pump some water up into a giant water tower. Why? The water goes down. spins the turbine, we get the energy back out, yada, yada, yada. We understand that. We've been using it for millennia. But the general dynamics. Heck, Archimedes still has a spiral that we use. It's basically the screw pump. But hey, we're very thankful, my friend. But all right, well, let's continue on with our little bit of reading because I skimmed this. Basically, long story short is I think they were using a silicon-based lattice, and what they were doing is since you have a limited structure, basically you can have crystal silicon, and you basically do photon, photon, photon. If you can measure all the events, and you've got an incredibly well designed lab environment, if you're just using electromagnetism, and that's basically all it is, you should be able to have very high precision. Now, if it is interacting within a lattice environment, I'm unsure because I believe just if it's just straight magnetic stuff, that's one of the reasons why we have like high confidence in certain electromagnetic activities up to about, I think 14 significant digits is QED. I believe so. You can check me on that. But all right, so let's go back. All right. I need some coffee. I've been rambling on. All right. The interaction of quantum emitters in photonic environments is usually described by open quantum system coupled to a reservoir that characteristics radiative and that characterize radiative and material loss. Such descriptions typically of cavity quantum electrodynamic cavity QED simplify the continuous electromagnetic spectrum via simple phenomenological model of the local density of states, and were very well suited for early high finesse micro resonators and Fabry Perot cavities that radiate weakly. Later, however, focus has shifted towards even more intricate photonic devices where extreme sub-wavelength field confinement leads to extreme light matter interactions. Such systems typically radiate efficiently to the far field, exhibit broadband and overlapping modes. Ooh, that's how we're doing this now, I think. And often have significant material losses. Classical models for the local density of states have been phenomenologically quantized to form an open quantum system by assuming Lorentzian photonic modes. Basically, just your energy equation. It's like, all right, what is that? Kinetic versus potential energy, or maybe that's is that a Hamilton? I always forget the difference there. Alternatively, classical and quasi-normal modes have been transformed and quantized canonically. However, such canonically, I think that means in order. So I think time does matter. However, such methods lack the generality of established quantum optical theory, e.g., like that. And their disconnect. Hold on, let's actually click on that. Four. Barnett methods in theoretical quantum optics, and the next one was okay, that review. Let's go back up. Oh yes, there's some pretty pictures in there. Well, we can skip ahead. We don't want to scare everyone off. Let's just finish reading this paragraph. However, such methods lack the generality of established quantum optical theory, read that, and the disconnect between the near and far field precludes straightforward descriptions of photon statistics, input and output field, squeezed light, dress states, etc. Furthermore, reservoir correlations from which complex non-Markovian dynamics arises are unaccounted for. Hence, there is a need for an a priori method that provides a global picture for open quantum nanophotonic systems. Okay. So if you're like me, you're obviously like, oh, what's a nanophotonic system? All right. That's okay. Anton gave us the link. It's the Wikipedia because it also sounds very relevant. Why? Let's go to our friend Wikipedia. Make this a little bit. There we go. All right, I'm beginning. All right. Again, links in doobly-doo. And nanophotonics or nano-optics is the study of the behavior of light on the nanometer scale. What is the nanometer scale? For 1 billion. All right, so 10 to the negative 9. Groovy. All right. It was either like 7 or 9. No, 7 is million, and then 9 is billions, or 9 zeros. And of the interaction of nanometer scale objects with light. It's the branch of optics, optical engineering, electrical engineering, and nanotechnology. Also, this involves dielectric structures such as nano antennas or metallic components, which can transport and focus light onto focus via surface plasmon polaritons. Surface plasma polaritons are electromagnetic waves that travel along metal, electric, or dielectric. Okay, so you're what is it, wave gradients or something like that. All right. Blah blah blah. Okay, so the term nano-optics, just like the term optics, refers to situations involving the ultraviolet and near-infrared. Okay. It's possible to squeeze light into a nanometer scale using other techniques. Okay, so we're doing squeezing. Experimentalists are basically wizards. Small volume. Okay. Miniaturization. Solar cells. There we go. All right. There's a bunch of stuff coming out on it. Hopefully, yeah, I saw this cool little thing. I listened to some of the ICTS's lectures because what is it? By the time I'm usually going to bed, they're usually doing their day / their lunchtime things. But I'll be in there listening, and I'm like, oh my god, wait, they're having it at what, picokelvin measurements now? They're doing literal wizardry that a lot of folks don't hear about. So I should actually, there's one person, I think they pulled their talk down because apparently their experiment showed like 20 orders of magnitude increased. I don't know. Maybe they pulled it down for a reason. I digress. Okay, so let's go back to. No, I was just showing that page. Okay. So there's no end to halving or doubling. Well, what if you just double in the other way? What if you just go around? What if their height, theoretically, if there was a minimum unit of space or length, maybe that's a minimum. Could you try to go beyond that? I mean, you could maybe wait. What is below there? I don't know. Darby dragons, aka maybe the Ruliad, maybe a higher dimensional construction that ends up inverting outward like a Clifford Taurus or something. Um, ain't that the question? But all right, so let's just get to a few pictures because this is absolutely fantastic. So exact quantum, yada yada yada. Okay. So again, it's only a few pages long, and it's like, all right, for papers, I can actually recognize something. Oh, I see h bar. I see the speed of the light. I see 2. I see the electric constant. I get some form of a unit of length in there. Oh, wasn't that we were just talking about? Imagine my shock. Okay, so we got some cool graphs. Let's take a look at this guy. What do we got? The graph of these. So that looks like the energy. That's the energy. Okay, modeling it out. Oh, groovy. Look. Oh, different peaks. Plotting. All right, pretty pictures. Okay, here we go. Now, I'm not sure where Anton got his picture from, but that's one of the reasons why I didn't necessarily just put it up there. All right. So these are the intensity distribution for A, the 504, and B, the 803 pseudo modes plotted as a function of 0 is less than R, and R is less than 1.5 micrometers. And I think that's 10 to the negative 6. That are those. Oh my God. Did I get those magnitude? What is mu meters? Hold on. Go to our friend Wolfram Alpha. Micrometer. It's the mu one, right? I don't want to be doing more fake science. Okay. Oh, excuse me. No, that's nanometers. Wait, nanometers? No. Oh, excuse me. No. Micrometer. Okay, it is a micrometer. Oh, yeah, because 1 micrometer is 1,000 nanometers. Okay, I'm sorry. I have Wolfram on the other tab. Hold on. Or not. Just go to window. There we go. See? I'm not just making everything up. Unless the curated stuff on Wolfram Alpha is totally wrong. Could be. I have some disagreement with it. But all right, let's go back to here we go. This guy. Yeah. Okay. So I mean, look at how pretty that is. Now what is this? You're like, oh, is this light? What is this quarks? Well, apparently we're looking at a I believe this is the silica lattice. Is that what it is? Uh, I mean, we would know if we actually read the paper and everything gone through. Let's see. Silicon. Oh, a spherical silicon resonator. Oh, that's why it looks that way, because it's a sphere. Duh. Okay. That makes sense. All right. So they're basically trying to take pictures and they're looking at the probability distributions of where stuff and things happened. Okay. And we have the intensity. And what are we using? We're using AU. That's angstroms. I believe angstroms. All right. So it's basically about 1 angstrom. So it's all right. About the radius of an atom. All right. Over there. Is well, the minimum above zero nerdy. Well, that might be depending on what you're talking about. I think was it if the Einstein kappa, which is related to allegedly the cosmological constant and everything like that. Apparently, if it's greater than zero, then we have de Sitter space. If it's less than zero, we get anti-de Sitter space. I don't know. Should we just be in like Sitter space? It's I'm just saying, what happens if they do net out to zero? I don't know. I don't know. Again, rampant speculation. Oh, hey Dan, how are we doing, my friend? You know what that reminds me? We're gonna speculate like this. Says what is non-Markovian? Yes, I have in the description. Yes, we conjecture ahead, but people come in at different times, and I don't know about you guys, but I don't always read what's in the description. I just come over. I'm like, oh, there's some people here. They're talking about some interesting stuff and things that I might be of interest to. So let me just click on this and see what happens. So we'll give our little disclaimer. So it gives me a chance to grab some more water. Where are we? Here we are. Disclaimer ahoy.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper-Rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyper-Rulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Full disclosure: this is a MacBook Pro, not a MacBook Air. We want to be as open and transparent as we can, right? All right. Random diatribe and highs aside, but damn, it's interesting because I know we had kind of talked about this before, and I was trying to learn, but apparently Professor Jacob Barandas may have taken all the fun out of quantum mechanics, or potentially just quantum theory in general. Hold on. What am I doing? Oh, I clicked the okay, remove that. Okay. But essentially, it's sounding like, because essentially it sounds like he even says at one point, it's like, well, I made an error. What was your error? It's like, I didn't assume Markovian dynamics. I didn't put a restriction on myself. It's like, wait a second, okay, so you did something wrong, so it's not going to work. The problem is he went through and it seems to work. He seems to, because he goes through line by line. And he's like, all right, here's your standard operator setup, blah, blah, blah. But we can phrase it in this way. And it's like, wait. So what you're saying, if we do non-Markovian, because essentially, to my knowledge, I believe it was assumed that you would need Markovian dynamics, and that was what you would use And if you didn't have that, it couldn't be included in a valid quantum theory. It's sounding to me, and again, just double check, but I'm looking at the guy's credentials. He seems to know what he's talking about. He's lining the things up. And I'm like, wait, so what you're saying is, number one, time matters. AKA, in order to get where we are, we needed a past. So in order to be in the present, wait. So what you're saying is the past is prologue, the future is now? I don't know. It's a very interesting thing to consider, but it's sounding like our degrees of freedom, the methods to get to a quantum theory that could help maybe bridge to general relativity or put things in a framework. It sounds like quantum theory is back on the table, folks. It's, but he admits that essentially, if you were to use this style or follow along this axiomatic branch, that he's like, you don't need your infinite dimension Hilbert space. You can have your infinite dimension Hilbert space. You can have your wave functions. You can totally use those things. We're not taking it away. It's just not required. So wait. If those aren't required, that would mean there would be additional ways to try to, I don't know, reproduce perhaps the standard model, provide an additional perspective in ways that maybe we could verify it. Maybe there's a couple of things in there. Maybe it's a little bit off. Maybe we can get a better intuition. Now, in order to do that, you would need a very broad, comprehensive theoretical framework. You're going to have to do a lot of work, and you're probably going to have to take years and years for somebody to go through and analyze the different constants of nature, the different metrics and everything, and to be able to reproduce a coherent, logical, comprehensive, and hopefully accurate framework. And it's numerology is numerology until you explain more with less, I claim. Okay. Because I know Dr. Unziker brings it up a fair bit there. It's like, oh, you're just doing numerology. You're doing numerology. Yeah, a lot of folks did numerology. Now we teach the stuff as the way things are. It's no, you have to be careful, because if you can start seeing a lot of pretty numbers, you can see a lot of pretty things, and the question is, okay, are you following because it's pretty? Or are you following it because it's revealing something new, or revealing? It's showing you the same thing in a different form that may be easier to digest, be able to conceptualize, and maybe we could better use that. Now, basically, show me the money. Show me the utility. What does it get us? Does it make things better? Does it help make things more accurate? Are we simplifying things? Is this something that we could explain to your average Sally, Dick, or Jane? Or do we need to stuff in an operator, a quantum cat, perhaps a nerdy rodent that's in a superposition of pickle and mouse form, and do we just throw all these things into a cosmic blender and we get off the slushy that is reality? That sounds oddly tasty, but at the same time, my stomach starts to churn a little, because I'd rather not have mouse, especially nerdy in my beverages. But well, Rick is commenting. Hey, Rick is commenting. The trick is to know what to not follow. That's I'd say that's a very good piece of advice, because if you start going down a particular path, there's also this. Okay, so there's something that they teach you when you are studying business in business school and stuff. Only undergrad, 5-year plan, full disclosure. Busy playing World of Warcraft. But there's a thing called a sunk cost. What is the sunk cost? It's like, all right, we're going to start. I'll give you an example. I started an office a number of years back, and I was going to work off of a contract of, at the time, I'm like, I looked at the amount people were getting per standard sale and everything. I'm like, all right, that much money. If I'm working under these folks that are getting that much money, I could legitimately do this for half of that payout. If you pay me 50% of that, I can actually make this work. The problem was, by the time we actually get some stuff up and running, we got the job, and we were hiring folks and trying to do all this, that, and the other thing, the payouts had dropped by like 40% or so. So all of a sudden, it's like, wait a second. The price that we were getting, it's almost half that. So what I would be getting would actually be half. So in order to do this and do all this work and what it was going to be, I'm like, this doesn't really make a lot of sense. Long story short, $20,000. Oopsie. Yeah, that was not a cheap one. But it's this whole thing where if you start getting into something and you invested, I don't know, you've written a dozen papers or maybe 100 papers, you're going down and it's like, all right, well, I spent all this time doing this. All right, I spent 5 years studying whatever maybe dead end it is. I don't know. Maybe it's interesting. Maybe there's a lot of mathematical stuff. Maybe you can produce beautiful graphs. Maybe fantastical hypergraphs that will be very engaging and such pretty pictures and everything doesn't tell us anything useful. That's I think what Rick was kind of hitting on the point there is if you can exclude your search space, that is huge. That's one of the reasons why perhaps analyzing something that I know Dr. Unzerker has brought up, like the constants of nature. A lot of folks, we talk about the speed of light in a vacuum. We talk about h bar, Planck's reduced constant, the elementary unit of action. And then we'll talk about Boltzmann's constants. It's like, all right, what is that? Oh, entropy, temperature stuff. Okay. What is entropy? It's all right. It's whatever that you don't really know how to describe it. There's something information, lack of knowledge. Just call it entropy. Why? Because nobody knows what entropy is, except for maybe Stephen Wolfram, maybe Boltzmann, God rest his soul, maybe Jennifer Scharf, and hey, maybe a couple people in the chat who are watching temporally in the future. But we got constants of nature, but we have certain measurements. Some of them are defined because we did the rework in 2019 to redefine SI. What did we do? Well, we had measured H bar to 12 significant digits. We lopped it off at 10 because the last two digits I think the error was like 6.2 or maybe 7.0. It was pretty large. I was like, all right, we have confidence in 10 significant digits. The speed of light. We've measured it in quotations because we actually measured the two-way speed of light to 9 significant digits. It is defined as 9 significant digits. I would try to say it. I always mess up on like the middle digit. Is it 299,700 and 2.9979 7.845? No, 5.45. Okay. That's what Wolfram Alpha is for. But okay, we have these, but those are main ones, and we have set those as definitions. Why? Because we've had very high confidence in our measurements for those digits. However, if you actually start going through CoData, you realize you got a lot more than like 3 constants of nature. You got your Planck units. You've got, at least on CODA, they have the Planck time, the Planck length, the Planck mass, and the Planck temperature. And then you got the energy equivalents and stuff. And then you get the relationship between those. And you get the anomalous magnetic moment of the electron. You got your G minus those. You've got your Hertz kilogram relationship. It's like, what the heck are these? Why are these here? Who the heck cares? Apparently people care. Why? Well, these are hard fought and won measurements from experience. Now the measurements, maybe they could be wrong, but that's why you want to have a lot of measurements. So now you can start to correlate them and you start to see how these things work. And maybe because not all measurements always agree, just because once you get to certain precision, I'm just going to throw a random magnitude out there, about 10 to the 7 or minus 7. Once you get about 7 significant digits into a lot of these measurements, there seems to be some deviation. Why? Why is that the case? Because if we know h bar to 10 significant digits, and we know the speed of light to 9 significant digits, why do we only know the Planck length and the Planck time to like 5? Oh, we've got 7, but they've got error in there, and some of the errors kind of big and stuff. So it's like, yeah, it's okay, but we would need multiple data points. But why is it with even like 288 dimensional fully different, or dimensionally different and or different numbers, do we have those measurements? Long story short, the poster over there has 288 different constants of nature over there. Why are there 288? It's not like it has something to do with the generalized volume of a tetrahedron or anything. That would just be weird, going back to the Platonic realm with five Platonic solids. Technically, there are 6 and 4 dimensions. But now we're really just randomly speculating and everything. But the interesting thing is, we have all these different measurements, and if they do have different magnitudes with different relations, why might that be the case? Could it be the product of 2 different Cartesian planes, something like the good Professor Jacob Barondess was saying? I don't know. I guess we're going to have to see what happens. Let's see. Yeah. Oh, there's a lot of all different types of stuff, nerdy. Well, yeah, pruning the tree that really does make a difference, because that's the thing. If you can eliminate where not to spend your time, you can better spend your time in other places. I just feel that not all. Some people get very involved. Like, it gets to the point, it's like, all right, oh, I'm a server first level 80 Death Knight in World of Warcraft. Oh, I have a Phoenix mount on a Dwarven Warrior, yada. You can do all these. Oh, you can sell your. Why don't I sell my account for all? Long story short, you end up spending so much time in something, you get used to spending your time doing it. So to do anything else might become hard. I feel like there's some certain social and human inertia to things. And also, we all know how great different human beings are at looking at their peers straight in the eye and saying, I was wrong. As long as people are able to freely admit that they're wrong, there shouldn't be a problem. Lacking thereof with sufficiently advanced evidence, or let's say sufficiently credible, verifiable evidence, that seems like, yeah, that sounds just more like a cult of personality. And I don't know. What else we got? Okay, Nerdy's saying that a paper isn't a paper without pictures. Graphs do count. Okay, I would tend to. I'm biased, but I the general thought of that does give me a good feeling. I do like pictures. As Nerdy's saying, you should stop looking at the two state vector formalism. Griswold is commenting on, I don't even know what type of I don't even know what a Skinner box is. I'm not sure I should want to know. I may have had to remove the guts that the cat left maybe about something. But we'll dance in Stonewood Foundation for oh, the good old days. I usually chilled an Iron Forge by the cart before I re-rolled Horde. But oh man, I digress. Ah, the good old days. Where were we at? Oh, maybe we should actually talk about let's go to Markov chains. Okay. Here we go. Well, maybe we should actually talk about what we were supposed to be talking about in the last 10 minutes. All right, let's bring this up, grab some water, and we will continue on, my friends. Sure are lucky on a planet full of water. We can even make it potable at that. God bless. All right. The Markov chain, link in the doobly-doo. In probability theory and statistics, a Markov chain or Markov process is a stochastic process describing a sequence of possible events in which the probability of each event depends only on the state attained in the previous event. Informally, this maybe is thought of as what happens next depends on only the state of affairs now, a countably infinite sequence in which the chain moves a state at discrete time steps gives a discrete time Markov chain, DTMC. Wow, it sounds like it should be on Joe Rogan. A continuous time process called a continuous time Markov chain, CTMC. Markov's processes are renamed in honor of the Russian mathematician Markov. Okay, statistical probabilities here. And we're going to let Thad take over because Thad looks extremely excited right now, and I think he has something to share. So I will talk it back. Yeah. Okay. All right. Okay. This previously tangent on Markov chains is interrupted by live science. Here we go. Okay. So we're talking about the two equiharmonic ranges in the gamma function, half periods in the gamma function. Ooh, yeah. Oh, all right. So let's do this. I think we can. All right. Yeah, because we're on the AirPods right now, Rick. So let's do this. Since it cancels out, let me swap to Mike. Here we go. All right. I just changed the thing in the middle. Hold on. Input. All right. La 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 la. Can you hear me? It's all right. Okay. So I think we should be good. All right. Can you all hear us now, or did I break the sound? Let's see. You can give us
equal harmonic half periods. Can you hear me? Can you guys hear me?
Let's bring.
Oh,
There we go.
the gamma function. I'm just rewriting this.
Okay, nerdy. There we go.
The gamma
All right.
function.
Yeah, just speak up just a little bit.
Okay. All right. So we have the first one, omega 1 equals something, which we'll get to specifically, but it's multiplied by the imaginary golden ratio.
Okay.
And the imaginary golden ratio, again, is -1 to the 1/3.
Yeah.
And the second equal harmonic half period in the gamma function is just the same something that's here.
Okay.
Before I get to that, what I want to point out is, because this is here, the difference between them, if we cube omega 1 and we cube omega 2,
Yeah.
they just become inverses.
That's right, because one is equal to
They become,
like one over
this
the other.
cube is equal to
inverses.
-1.
Yeah, you see one.
Yeah.
Yeah.
So omega 1 cubed equals minus omega 2 cubed. That's not a discovery or anything. The point is, there's this special place in the gamma function where both of its equal harmonic half periods equal their own opposites as cubes.
Okay.
Okay, now that special place I just found is the only thing that matches with all the digits for everything in the poster
Yeah.
for the mass of the Triton.
Okay. All right.
That's the division spot for the mass of the Triton, I now believe. So anyway, that was the exciting thing, just to see this symmetry spot. Oh, now let me fill in the question marks. Okay, so the question marks are, let's see, gamma cubed of 1/3 over 4 pi. And this one, yeah, same thing, omega 2. So the place in which the inversion happens is already a cubic division structure to begin with. Beautiful. And over the sphere.
Okay, so what just happened?
So these are the known equine harmonic half periods of the gamma function. Okay, this is the place where the Weierstrass elliptic function becomes equal for both stretches. Okay,
Yeah.
so in this spot, there's a special spot in the structure. If you're trying to visualize the structure of the gamma function, the way it's dividing the world and so on, try to imagine the world divided under the code of the gamma function, then you'll be delighted to discover that the gamma function has in this equiharmonic case spot in it, right? A perfect cubic inversion, a symmetry here that's cubic. Anyway, I think that's really good.
And the only difference between these is the imaginary golden ratio.
Yeah.
Which is
Another
the
cool
cubed
thing,
root of negative
So
1.
this special point in the gamma function also depends on the imaginary golden ratio. So the gamma function has the imaginary golden ratio built all over in its symmetries, right?
and then when we cube that, we get that.
Yeah.
So we're basically just getting out the imaginary golden ratio.
If we divide this one by this one, we get just left over the imaginary golden ratio.
Oh, what I'm saying is that the only difference between them is the imaginary golden ratio.
Yep.
That would be where the cubic thing would
That's-
come out. Yeah.
Yep.
That's very
But
cool.
the thing we need to cube in order to get to that balance point is already gamma cubed of 1/3. Anyway, it's just a beautiful symmetry thing. It's now the best answer that fits. So I'm trying to believe it and understand it, but I'm currently just in awe of the cubic symmetry of this location in the gamma function.
So I'm going to go with, well, this is why evaluating data, especially a ginormous amount of data, may be very useful, because it might take literally years to go through and then eventually be like, wait a second, here's a relationship. What's the only difference here? Oh, the cubed root of -1. So when we cube it, we get this and everything. And if it's for the Triton, that may help us with other things too.
Which also
Yes,
yeah, that's cool.
3 is implied.
Where it's now going to sit because of this answer, it's also times r cubed. Okay, so that puts it right next to a whole bunch of other things that are cubes. It's all a cubic story in that part of the story, so part of the poster. So I'm going to try to get really clear on that now. It's connecting so many things.
Hey, K-Shell. And Rick is commenting, cubic inversion is part of multiplying on elliptic curves.
Yes.
So yeah, okay. That seems all check out.
It's the elliptic Weierstrass equiharmonic.
Oh, Weierstrass strikes again, the wizard function.
Yes.
I like it. Dan is commenting, the structure is built in. The imaginary golden ratio gives the third dimension. That's a very powerful claim. I mean, mathematically, that's mathematically, I mean, that does kind of seem correct.
It seems to be required if you divide that way.
He's not. They just thought you were. They thought you were from 60 symbols. They thought you were number filed. Oh. 60 symbols is number file's other channel. But Rick is commenting, elliptic curves, complex tori conjectures ahead. I think that, I think that that seems like a very good place to look.
Yeah. Anyway, that's it. It's beautiful and short enough. I don't think I need to do more, but that's fun.
No, that's good. No, we were just talking about how you can have a sunk cost and stuff where basically you spend so much time doing something where basically it's just like, all right, well, this is the thing we do. This is the thing we do. It's like, well, here's an alternative, and maybe it explains more with less, but this is what I'm doing. Basically, when presented with extremely accurate, better evidence, and you just kind of ignore it because, well, I'm already invested in this.
Yeah.
Being able to close
true,
off
that's
paths.
true. But when you get a clear enough story that you can give the answer to somebody in a way that just totally makes sense, and the rest leans to make sense of the other story they're holding on to, then it's natural for them to let go of that one because this makes sense of what I'm trying
well,
to
see, that's why I don't like, because a lot of times people just like to say, well, people are wrong, people are just making stuff up, whatever it is, blah, blah, blah. Now, I mean, hashtag not all, but I'm sure some of that is true. But it's one of those things where human beings are gonna human. That's a thing. But if we can exclude certain spaces, like, okay, maybe this isn't a good space, because basically we have measurements for the different constants of nature and everything. So we actually have excluded spaces. Now maybe we need to go up several sigma.
We are all making it up, and that's the point. We're all making it up because none of us know the answer, and we're all blind to the truth, and we're trying to use guides to get there, right? But if we're not using good guides, then what we're making up shouldn't really be listened to. And the point is, we have a clear metric for what's good guides. We have science. We have the things that we've measured, the features of the world that we're trying to make sense of. That's the story you need to search for. That's the thing we need to be making up. Right? Until we get it. Because why? Because that's the story that empowers us. There's lots of stories you can make up about the world that give you political clout or make you look a certain way or whatever. But when you make up a story about the world that's right, that clarifies actual essences of the world that you couldn't see in other stories, then you gain new powers. You can do new things. You can work less, for example, because you have something that can do the work for you, like electricity. Yeah. So anyway, ranting, but
no, very, very cool, very relevant. It helps me feel better about all the time I spend ranting about random tangents and everything. This is just basically on point, I guess, pun intended.
Yeah. Anyway,
cool. So I think
I think on here.
Let's see. I got about 30 folks watching between, whether it's YouTube, Twitter, and everything. You make a Markov chain with one. Well, that leads. I don't know. We may be able to. What is it? They're both very discrete. Yeah. Okay. I think. Well, people having a good time. I think we'll leave on a high point. So we put it in our hour. We got a little bit of some live actual science rather than me struggling through trying to explain a Markov chain. Maybe we'll do it tomorrow. But until then, peace out, everybody.